Good evening, sir. My name is Augumented. We are going to take you through Retrieval Augmented Fine-Tuning, that is RAFT. Together with me is the co-presenter, that is Katende Haman, who will be presenting after me. So to talk about Retrieval Augmented Fine-Tuning, that is RAFT. RAFT is a technique in machine learning that enhances predefined models by combining them with a retrieval mechanism during fine-tuning. These predefined models, I am talking about the models that have been trained on a larger data set and can be used for specific or different tasks, depending on the preference of the user. So this RAFT is primarily used in natural language processing, tasks such as maybe answering questions and information retrieval automation, but a few. So the core idea behind the RAFT is to augment the model's pre-existing knowledge with relevant retrieved documents or data during fine-tuning phases, instead of solely relying on the information contained within the model's parameter, instead of relying on the information that has been maybe recorded, memorialized. So it retrieves documents or data during the fine-tuning phases. What is contained with the information, what is contained within the model's parameters. The RAFT allows to search and retrieve additional content from a larger external sources. External sources here can be maybe the books, articles, different articles, or depending on which problem you want the model maybe to address. So here, I'm going to take you through the diagram that you're seeing on the screen. This diagram here compares the three different approaches to handling knowledge in artificial intelligence models, as you see them divided in three. That is the closed book, open book, and the RAFT. That is the proposed, which is now the final what? The final approach. Now, in the closed book, as you see it, the closed book model is trained with all knowledge baked in. The knowledge is baked in, or it is what? It is refined. That is basically a closed book. It does not access external sources. It relies on the memorialized information. As you see it here, the approach does not access external documents. Once trained, it relies only on what has been memorialized. That is what I was telling you, which may lead to maybe outdated or incomplete responses, since it only deals with memorialized information or documents. Now, it cannot expose it to newly information, which is maybe updated or adjusted, fine-tuned. You get it? Then when you look at the second approach, that is the open book approach. Now, open book approach, this is the middle approach. Now, with the open book approach, it allows access to external documents at testing time. During time of testing, it allows access to external documents. The external documents, as you see here, this could be different sources, can be articles, they can be Wikipedia, magazines, depending on which information you want it to address. So when it accesses those external documents at the testing time, instead of relying solely on pre-trained knowledge, it retrieves relevant information from such external databases before answering any given maybe aspect and maybe any question asked. Example here, I give you the real time example I can give you is the retrieval of augmented generation method, like the chat GPT with the web search, where we always ask a lot of questions and it instantly checks different sources and gives us what answers which are up to date, not like in the first approach of closed book, where it only depends on what memorized information. You get it? That is what open book does. Now, from open book, we move to the RAFT. The RAFT is now the third what? The third approach. Now, with the RAFT, the proposed approach, that is the RAFT, it is improvement over the open book. Instead of just maybe using external documents at testing time, the RAFT teaches the model how to integrate retrieval into its training. The model learns to better incorporate retrieved knowledge into maybe its responses, improving what? Generalization. So the process, in the RAFT process, it involves queries. That is the retrieval of external what? External documents. Then fine-tuning. The model uses these documents now. It fine-tunes these documents. The model learns how to use the retrieval effectively at test of and at the time of what? At the time of testing. This makes the model more adaptable to new knowledge, while still benefiting from the retrieval-based argumentation. That is all about this table that you're seeing on the screen. The three approaches: closed book, open book, and RAFT. Now, RAFT is a combination. It combines, it picks the knowledge from external sources, as you can see. So in summary, in a closed book, there is no access to what? External sources. Then also it does not learn from retrieved documents. Then in open book, there is access to external sources. Then also it does not allow retrieval of information from documents. Now, in a RAFT, it allows all the three. There is access to external sources, allows retrieval from other documents. It allows all the two, actually. Now, the RAFT bridges the gap between closed book and open book approaches by training models to effectively use retrieved knowledge, leading to better artificial intelligence. The next thing here, I'm going to take you through how RAFT works. I'm going to take you simply on how RAFT works. The model queries an external knowledge base. Example, the vector database, APIs to retrieve relevant what? Now, the AI searches, when you talk about RAFT improving AI by letting it retrieve, it searches and retrieves, uses and learn from external information, rather than relying on what it was trained on, what it memorized when it was being trained. So for it retrieves, uses, and learns from external information as well. So let me talk about argumentation component. With the argumentation component here, this is all about adding more context. The retrieved information is attached to the user's input. The retrieved information is attached to the user's input. Before passing it to the AI model. It is first passed to the user's input so that the user can appreciate whether what is being input, he appreciates whether it is in position to answer what he or she wants before it is passed to the AI model. Example, if you ask about climate change, the AI first fetches the recent search papers and the answer and then answers using those details. Take for example, if you ask about climate change right now in 2024, I mean 2025, it first searches about the recent papers, maybe those of maybe December 2024, and it uses that information. It relies on that information to answer you. Then this fills in the gaps where the base model may not have seen the information during what? During training. You get it? Are we together up to there? Then we talk about the fine-tuning component. The fine-tuning component here, this one, it learns from the new knowledge. The AI is trained again using the newly retrieved and augmented data. Instead of just using it is old knowledge, the AI now learns from the latest, more relevant data, which has been the one which has been fine-tuned. Adjustments have been made to fit the specific tasks of the what? Of the user. So the AI is trained again using the newly retrieved and augmented data instead of just using the what? The old one. So the step here improves accuracy. One is that it improves accuracy because now the information will have already been adjusted. It makes it improve in accuracy, efficiency, and generalization, making AI a bit smarter now compared to before. It makes it smarter by giving you up-to-date information. It gives you accurate response, which is up-to-date and latest. Now, in summary, retrieval here, retrieval it is all about finding relevant information to the inputs for better responses. Then fine-tuning, AI updates its knowledge to improve what? Accuracy. That is all about that. Now, let me take you through this other diagram. This is a diagram. This diagram represents the process of training and fine-tuning a larger language model using both general web data and specific private knowledge bases. Now, it is broken into steps. That is, you look at the big web data, the base large language model, then the fine-tuned large language model. Now, with web-based, with big web data, that is the pre-training phases. The process begins with the larger scale web data. Example can be Wikipedia, the books, articles, research papers, as we talked about in the previous slide, can be research paper. Now, this data is used for pre-training, where the models learn general language patterns, the facts, and the reasoning abilities, different reasoning abilities. You get it? That is what the big web does. It begins with the larger scale web data that I have talked about, the research papers. Then the data is used for pre-training, where the model learns general language what? Patterns, facts, and the different reasoning abilities. Then you move to step 2. That is the base large language model. Now, after pre-training, which is done in the big web data, after pre-training, we get the base LLM. That is the general purpose language model, like maybe BAT. Can talk of BAT. This model can generate text and answer general questions. It generates text and answers now what? General questions. But it will lack the domain-specific knowledge. You get it? It can be in a position now to generate text and answer larger questions, but lacking the domain-specific knowledge. Now, here you look at the specific or the private-based knowledge to make the model more useful for a specific use case. Example, maybe medical or the legal department or companies, specific data. The private data set is then what? Introduced in this step. Then this data set will contain the domain specific information now, not present in the original data training. Now, at this time now, it will contain what? It contains the original data, what? Training data. Which, I mean, it will contain the domain-specific information, I beg your pardon, which is not present in the what? Original data training. Now, in this process again, the process undergoes what we call supervised fine-tuning. The base LLM is fine-tuned using the private knowledge now, which is containing what? The domain-specific information. So it is fine-tuned through supervised learning. Now, this step ensures adaptability. It adapts to specialized technology. I can talk of the unique data sets that may be introduced in there. Then now, this one leads you to the final step, that is the fine-tuning LLM. That is the third step. Now, in the fine-tuning LLM, the final output is then fine-tuned. The final output is a fine-tuned LLM that can answer now the domain-specific queries which are being generated by the users. The specific queries, example here, I can give the legal LLM fine-tune. On court case data, can provide better legal advice than a general model, because now it is up to date and it has been fine-tuned. You get it? So that is all about this diagram. It was able to represent the process of training and fine-tuning a larger language model with both general web data and the specific private knowledge bases. So allow me take you through the advantages of RAFT. RAFT makes AI models smarter. After all those processes, it makes now AI models smarter by retrieving real-time information instead of only relying on the past training, which has been memorialized. So it makes now it smarter after doing the fine-tuning, whereby it is able now to ask many questions and give accurate answers. You get it? Depending on the need of the user. So here we are going to talk about domain-specific expertise. With domain-specific expertise, it prefers for specialization of what? Specialized fields. It is so perfect for specialized, perfection is in specialized fields. Take, for example, fields like medical, law, and maybe finance, to mention but a few. Now, new knowledge is constantly evolving in here. That is another advantage of RAFT. It allows new knowledge to constantly do what? Evolve. RAFT can retrieve and use the latest industry-specific information, making it highly reliable for professionals. Since it has undergone all those processes of fine-tuning, so accuracy is now there. So it makes it highly reliable for professionals, since it retrieves and allows use of latest industry information. Example, a legal AI assistant using RAFT can pull the latest case laws. It can search for those sources through the external sources. Then it pulls it pulls the latest case laws instead of relying on the outdated legal texts. You know, there are a lot of amendments, and when the fine-tuning is done, it looks for the latest sources which give up-to-date information. So that is another advantage of what? Of RAFT. Then talking about improved what? Improved accuracy. Uh, with improved accuracy, here the RAFT it now generates it does what they call hallucination. That is generating misleading or false information. RAFT grounds its responses in real retrieved data, reducing what? Reducing errors. Since it has now been fine-tuned, it now retrieves that information and grounds the responses in real retrieved data, not again relying on the past data. It is now on the real retrieved data, which reduces errors. These errors will be minimal now compared to the old data that has been that was memorialized. Yes. Example here, if you ask regular AI about new scientific discoveries, it might make up it might make up facts about RAFT, fetches real studies to ensure what? To ensure accuracy. Now, let me talk about efficient training. With efficient training, less computations or more speed. Traditional fine-tuning requires updating many parameters, just like I've talked about. It requires updating a lot of parameters, which is costly and time-consuming. So what RAFT does, it only fine-tunes with retrieved data, reducing the number of parameters that need updating. It only fine-tunes with retrieved data, not again repeating, fine-tuning the whole data. It only fine-tunes retrieved data, reducing the number of parameters that need updating. Example, instead of maybe retraining a whole AI model from scratch. Now, what RAF does, it only updates specific parts, making it much faster and resource efficient, making it much faster and resource efficient. So in summary, what RAFT does, it is better in generalization, domain-specific expertise, improved accuracy, and efficient training. So in brief, those are the advantages of RAFT. So at this particular moment, sir, allow me welcome my co-presenter to take you through other parts of our presentation. That is the implementation and other things. Thank you so much for listening to me. Thank you.
Yeah, so my name is Katende Haman, and I'll be taking you through the implementation of RAFT. So RAFT is implemented in four major steps. The first step is select a retrieval system. So a retrieval system can be a way of retrieving information that you're going to use in the retrieval augmented fine-tuning. It is just a way of selecting a way of you're going to retrieve the information. So you can decide to retrieve the information from a database. You can decide to retrieve the information from a web source. You can decide to retrieve information from different articles. The next step is to prepare the training data. Remember, these are still machine learning models, meaning they still have to have a data set for training them. So you generate an augmented example with retrieved context. That is, get the retrieved context and then get the retrieved information, then get the data set in place for training. Then the third step is fine-tuning. Fine-tuning with augmented data. So you train using frameworks like Hugging Face, OpenAI fine-tuning APIs. Then the fourth step and the last step is evaluate and optimize. Evaluate and optimize. This is get to understand how your model performs using tools like F1, which will tell you how your model performs. So next, I'll take you through a code implementation of how you can try to implement RAFT. So first of all, we shall import the required libraries. That is, for example, sentence transformers, FICE, and then NP. NumPy. So these modules or these libraries, for example, sentence transformers, this library will help you with making embeddings from the text that you've imported. FICE is a fast similarity search, which will enable you store and then quickly retrieve information from a database. And then NumPy will provide arrays for preprocessing during the implementation. So first of all, the first step is load the embedding model. For this case, for example, we've used L-mini L6v2, which is a pre-trained model. Remember, we said a pre-trained model is a model that is already trained on a large data set and can be used for different tasks. So after loading the pre-trained model, here we use a sample document that would pass into the model for embedding. And then this document will act as the current knowledge base. So this line will help us convert the model, or will help us convert the documents into vectors or embeddings, which are just easy to work with during this kind of processing. Then here, this code snippet helps us create a FICE index. A FICE index is to store the documents and then quickly retrieve the documents when needed. Because FICE is quick is a fast search similarity search, fast similarity search index for data processing, excuse me. Then query retrieval. So this is the query. For example, this is the query that we've got from a user. So this query has to be embedded, passed into the model, and then retrieve the most relevant search compared to the most relevant response compared to in comparison with the query. Then so when you get the retrieved response, here in our case we've printed it out on the terminal. So this entire code is just about, remember we said selecting a retrieval mechanism. So here we've selected FICE, which is our retrieval path, because it stores and can quickly help us retrieve the information. Then the other thing is to select, to prepare pre-training data. So here we've prepared pre-training data by uploading a pre-trained model, then fine-tuning. So we are going to fine-tuning. So this code snippet is for fine-tuning the model. So for fine-tuning the model, we'll need libraries like training, the trainer, like a training arguments, and then the auto arguments, auto model for casual, LMA. and then auto tokenizer. So, and then libraries like touch. So these first libraries you see, for example, the trainer and training arguments that are used for training the model, auto model for casual, and auto tokenizer are used for tokenization. Tokenization is like creating tokens from the different texts. So after importing all those libraries, you load the pre-trainer model and the tokenizer. So the pre-trainer model that we've used is Distill GPT-2, which is an open source GPT API that we can use for this kind of assignments. So we pass the model to the auto tokenizer and then pass it to the auto model for casual. So this entire process is just loading the pre-trained model. Then retrieving, get the retrieve text from FICE, because we said a FICE has an index that stores and then quickly provides that information at the moment that you want it. So after getting this retrieved information, prepare it for training by passing it into this library. By passing it into this library for training it, then tokenizing the data. Tokenizing is, we said, is creating different texts and then passing it to the train data sets such that it can be the model can be trained on that kind of on the data set. So this entire thing is the other step in our implementation of the RAFT, is that we've loaded the pre-trained model, we've prepared the data for training, and then we've trained the data using we've fine-tuned the data using the hanging face trainer API. So this is how, in simple terms, you can implement RAFT. So further, I'll take you through a brief difference between RAFT, RAG, and then the standard fine-tuning mechanism. So for RAFT, for a feature that is data dependent, RAFT here, external data retrieving is done during training. Data dependent. External data is external retrieval during training, meaning the data gets the model gets the data during the training process. Then RAG, external retrieval at inference, meaning when you ask the model to give you a response, it will at that moment retrieve the information, the data, then provide it to you. Then for a standard fine-tuning, this is where the model is retrained over and over. It will just have a static data set, meaning it will only give you information from its knowledge base. Then knowledge updates for static fine-tuned model, like the normal machine learning models, it will require retraining. If the knowledge is, if information is updated from the source, this model will require constant retraining over and over. Then for RAG, it will dynamically update since the information is retrieved at inference. The moment you want it, it is referenced. Then for RAFT, it will have enhanced learning with retrieval, meaning it will still have the knowledge base, but then go on to retrieve that information that you want. Then accuracy, this one, the fine-tuned, the normal fine-tuned model we may give you inaccurate results. The RAG will have less accurate results, but then the RAFT will have more accurate results. Then you will find that all these other models will have a high or moderate cost during computation, but then for RAFT, it will have a lower computation cost. So the challenges of using RAFT is that we have computational costs. For example, because we said it will have a lower, not zero, because fetching data using fetching and using extra data requires more processing power, and then data quality, because we are retrieving this information, we don't particularly mind on its quality, mind on its source. We just mind on giving the user a response. Then implementation complexity, you will find that implementing this fine-tuned model may be a little bit complex. This is group 7, group 7, portion 1, and we have been covering retrieval augmented fine-tuning. Thank you.